I am practically sure that you have seen complex numbers before, so this introduction will be just a little bit of a refresher of what you've learned, as well as maybe discovery of a couple of new things about complex numbers. Of course, we're going to look at complex numbers in the context of linear algebra, so that is where our focus is going to be. But again, just as part of the refresh, remember that a complex number is not a complicated number like the one you have in front of you. In fact, probably you'll recognize that as an approximation of pi. And a complex number is not some number that has been drawn in a very complicated way with all kinds of ornaments, nor is it a number which is made up of complicated formulae with all kinds of messy steps in between. So what is a complex number? Well, in order to look at a complex number, we have to go back and refresh our memory about what was the motivation for developing complex numbers. And the motivation, of course, is the fact that the equation x squared plus 1 equals 0 does not have any real solution. There is no real number whose square, when added to 1, gives us 0. In other words, no real number whose square is negative, because of course any real number we take, once we square it, it always becomes positive. Alright, so the idea was, let's invent one. So we don't have a solution to this equation, so let's pretend that we had one and let's see where we go. It turns out, of course, that this idea of trying to invent this number has proved very, very fruitful in all kinds of areas of mathematics as well as in applications. We may call them complex numbers, and as we're going to see them in a minute, imaginary numbers, but there are many concrete applications of imaginary and complex numbers to real life. So what we're going to do is we're going to say, all right, let's call I a number which has exactly this property, meaning that its square is going to be equal to -1. So what we're going to do is we're going to call I and all its multiples imaginary numbers. Again, they're imaginary because they do not exist among the real numbers, but once again, I don't mind insisting on this quite a bit, these numbers are not imaginary in the sense that they lead only to imaginary applications, they lead to very concrete applications. Once we have imaginary numbers, it's easy to define a complex number. It's just the sum of a real and an imaginary number. So what do we mean by that? So a complex number is a number that looks like this. Z equal A, where A is a real number, plus B, which is another real number, times I. So what you have here is a sum of two pieces. One is real, number A, and one is an imaginary number, namely BI. And we're going to call this sum a complex number. The notation, the customary notation, is to use the letter Z for it, just to identify the fact that we're not dealing with real numbers. However, in some situations we may need to use other letters, and we will. Now that we have defined complex numbers, we can do usual algebra with them. We're going to call it complex algebra simply because it involves complex numbers, but it's not complex again in the sense that it is complicated. So what can we do with numbers? Well, we can add them. How do we add two numbers? Well, you take two complex numbers, A plus BI and C plus DI, and we're going to add them in the usual, reasonable, intuitive way. We're going to add the two real components together, giving us A plus C as the real component, and we're going to add the two imaginary components together, giving us B plus D times A as the imaginary part, and therefore the sum of these two numbers is going to be exactly what you expect it to be. As a very simple and immediate example, let's say that we want to add 3 plus 2i and 2 minus 7i together. Well, all we have to do is add the 3 and the 2, that gives us a 5, and then we can do the 2i minus 7i, that gives us a minus 5i, and therefore the sum of these two is going to be 5 minus 5i. Now we could factor that 5 out of there and write this number as 5 times 1 minus I, but there is no practical purpose, no practical advantage in doing so, since a complex number is still going to be given by the sum of a real and an imaginary number. However, this gives us another idea. What we can do is we can multiply a complex number by a scalar. And here we still by a scalar, we mean a real number. So the way we do it is we take, again, we do it in the usual intuitive and expected way of taking a scalar k and multiplying it by c plus di, simply by multiplying c by k and di by k. And notice that again, k and d are both real numbers, so they can be multiplied together. For instance, as an example, let's say that we multiply 4 times 3 plus 2i. That gives us very duh way, 12 plus 8i. Not much complicated with that. But notice now that when we're dealing with these complex numbers, at this point we have both an addition and a scalar multiplication. And so the question might be maybe asked, well, are we dealing with a vector space? Because, of course, these are the two closure axioms of the vector space, and because of the way we've defined them, by adding two complex numbers we get a complex number. Multiplying a complex number by a scalar also gives us a complex number. Now there are still the other axioms to check, but you should be able to see that since the other axioms all come from real algebra and we're not doing anything really different here, they are going to work as well. So in fact, do complex numbers form a vector space? Yes, and it's a vector space that we're going to denote with the letter C, with this usual weird font similar to R. And it's a vector space which is actually isomorphic to R2 as a vector space. It also has additional properties of its own, but as a vector space, it's isomorphic to R2. How do we get the isomorphism? Remember, what is an isomorphism? It's just a correspondence where each element of C has to be corresponding to an element of R2, so that the way we present it is different, but the way they act and they work is exactly the same. And of course, the way we do it is the obvious one of associating a complex number a plus bi to the vector, the usual Euclidean vector ab, and then the vector addition and scalar multiplication are the same. And because of this isomorphism, we can see that in obvious basis, a standard basis for C is going to be made up of the two numbers 1, which is going to be the basis for the real part, and I, which is going to be a basis for the imaginary part.